Well, good morning, everybody.
Morning.
How's everybody doing?
Yeah, kicking.
Kicking, huh? That's good. That's good. First day of class. Glad to see everybody. Just so that everybody's clear, I am recording these. So at the end of the session, I will upload these onto YouTube, and there will be a link within Canvas to where you can go back and view them. There's a couple of reasons that I do this. Number one, from time to time, especially during COVID, you might get ill. You don't want to get behind. You'll be able to see what's there, okay? I do want to say that the camera's not going to record everything we do on the board, though, but it will at least capture the voice, and there will be closed captioning that's provided by YouTube on that. So, but most of the time we'll have at least some things on the screen. So, you know, it's not perfect, but it will we'll do the best we can with it. So, what I want to do this morning, we're going to cover these things today. I'm going to introduce you to the course. We're going to talk a little bit about some syllabus items, okay? I'll make sure that everything's clear there for you so that you're off to a good start this semester. I'm going to give you a little bit of an introduction of why organic chemistry is important. Okay, some of you are probably wondering, why do I have to take this class? I'm going to try to dispel some of the myths about organic chemistry for you. And then we're going to give you just enough Chemistry 107. Okay, unfortunately, the prerequisite to this class is Chemistry 106. Really what you need is some topics out of Chemistry 107. So I'm going to give you just in time, what we call just in time teaching, throughout the semester on any topics that you might need from Chemistry 107, okay? So I'm not going to throw you to the wolves with that and tell you to go read your old book and yada, yada, yada. I'm going to give you what you need from Chemistry 107 when those topics are required, okay? So I thought we would take a moment and introduce ourselves. Tell me your name and your major.
My name is Jason. I'm a forensic science major.
Colin McDonald, when I was an adult, forensic science major with an aspect of biology and a minor in criminal justice.
Okay.
I'm sorry, Equilibria, I'm a laboratory science major.
You're a what major?
Laboratory science.
Laboratory science, MLS? Okay, great.
Sarah Hill, I'm a forensics major.
I'm Cassie Walter, and I'm a forensic science major. My name is Lydia, and dietetics is my major.
Dietetics, okay, great.
I'm Maddie Bennett, and I'm an MLS major.
I'm Margot, and I'm a dietetics major.
I'm Bailey, and I'm a dietetics major.
I'm Felicia, and I'm an MLS major.
MLS?
I'm Haley, and I'm also an MLS major.
I'm Jenna, I'm an MLS.
I'm Cassie, I'm forensics.
My name is Kimberly, and I'm a nutrition and dietetics major.
I'm Miranda, and I'm forensics.
My name is Selena, I'm a nutrition dietetics.
My name is Kate, and I'm a forensic science major.
I'm Rose, and I'm majoring in MLS.
MLS? Okay.
My name is Dallas. I'm an MLS major with a minor in psychology.
Keq McNeil, forensic science major.
Okay.
Sydney and Lane, and a forensics major.
Victoria, forensics major.
Colton, dietetics major.
Brielle, forensics major.
Kaylin, forensic major.
Caitlin, forensics major.
Oh, wait, both Caitlin?
Caitlin and Caitlin.
Oh, Caitlin and Caitlin, okay, all right.
Yeah.
I have to keep that in mind.
I'm Jessica, and I'm a nutrition and dietetics major.
Okay.
Bianca, nutrition and dietetics major.
All right, well, welcome, everybody. Just for full transparency, I'm terrible with names. I will forget your name, and I don't take it personally, but I will remember your face. So I typically have lunch a couple times a week over in the Fresh, and I quite frequently run into students from time to time, and so if you say hello and I say hello back but kind of struggle to remember your name, please don't be offended. I don't mean to be a lot of people's names, and I'm just not particularly great at it. But I do want to try to get to know your name. I want to try to get to know who you are. I want to try to get to understand your goals in life, because organic chemistry is going to help you attain those goals. And so let's go ahead and get started and talk a little bit about the course. So my name is Dr. Douglas Masterson. When you signed up for this course, you probably saw that it had said Dr. David Hayhurst. Sadly, Dr. Hayhurst passed away this summer, and so his teaching load had to be obviously redistributed. I am an associate provost. I'm a chemistry professor. My specialty is organic chemistry. It is discipline-wise, it is the love of my life. I really like working with organic chemistry, in organic chemistry, all of the concepts with organic chemistry. It's what I'm passionate about in the laboratory, and hopefully I can bring some of that across to you this semester. I don't expect any of you to take on the passion that I have for it, but I hope you at least leave with an understanding of why the various majors that you all mentioned require at least a fundamental understanding of organic chemistry. So that's really what this course is. This is not Organic Chemistry 1 and 2, as we call it. This is an introduction or the essentials of organic chemistry. And so we're going to cover a wide variety of topics, but just about that deep, okay? So instead of knowing 1,000 different reactions that we would expect somebody who's advancing their study in organic chemistry to know, we're going to keep it simple to the basics, to the things that you really need to know so that you can move on in biochemistry and have the foundation that you need for your particular major, okay? My office location, I am in the International Center, room 517. So the International Center is the building over by the Baptist Student Union. It's between the Baptist Student Union and the Liberal Arts Building, okay, so right over there. That is where I'm located, again on the 5th floor. You'll go to what is called Suite 517, and then my office is within that. But if you go into 517, you'll be able to find me, okay? So there's my office phone number, 266-4714. I'm going to have office hours set aside on Wednesday for 3 to 5. What does that mean? What do office hours mean? Office hours means that those are times that I am setting aside that you all can just walk in without an appointment. However, it is best to make an appointment. Okay, if you're on that side of campus and it's Wednesday and it's 3:30 and hey, I'm going to stop by and talk to Dr. Masterson for a second, feel free to come on in. But please know that office hours are not where I don't do anything else, because I know that a lot of students don't come and use office hours. I hope you prove me wrong on that, okay? But I will have other things that are going on, so when you come in and I will stop doing what I'm doing, and we will have whatever meeting we need to have if you decide to come to office hours. Probably the easiest way to get in touch with me is through my email, douglas.masterson@usm.edu. Okay? And so the text that we have this semester is the Introduction to Organic Chemistry. It's by Brown and Poon. I have to admit, I'm not a huge fan of this book, but it's the one I got stuck with. Last minute teaching, so we're going to struggle through it together. But it's good enough. I mean, it's going to get you what you need. You all already have access to that in the Canvas shell. Okay, so if you go into the Canvas shell, under the student view, the first day program, you have access to that textbook right now. So you can go in and take a look at that. Now, if you're like me and you want a hard copy, you'll have to purchase that separately. That's completely up to you. The electronic copy is perfectly fine for the things that you're going to need to do in this class, okay? If you so desire, I am not going to require you to purchase a model kit, because obviously I took over the class late. I'm going to try to remember to bring some model kit pieces and we'll work together in groups doing a few things. But if you have a little extra money and you're thinking, it'd be helpful, I would recommend you buy a model kit, okay? And they're about $28. You can get them on darlingmodels.com. I don't think they have any over in the bookstore because, again, they weren't recommended for the class. But one of the things that you need to understand about organic chemistry is structure is function. A molecule does what it does because not only of its composition, but because of the shape it has. And, it's hard to understand shapes in your mind. It's hard to understand it on a two-dimensional piece of paper. Some people are really good at it. I still build models. It's easy to get things backwards. So, in our tutorial center, does everybody know where the tutorial center is? Over in Walker Science. I forget the room number. It's on the second floor, but there is a tutorial center, and they have plenty of model kit pieces as well. So I would highly recommend, if you don't want to buy a model kit and you find yourself struggling with shapes and things like that, go over to the tutorial center, get a tutor, sit down and play with some models. Now, I will allow the model kit on the exam if you have one. But I am going to try to keep exam questions with 3 dimensions in mind to a minimum, okay? But there are a couple of chapters where 3-dimensional stuff is important. So if you want to buy a model kit, you can actually get one cheaper. That's $28 just for one in the nice hard plastic case. They've got one that's in a bag, and I think it's less than 20 bucks. But it's the same model kit, just not as fancy a way to carry it around, okay? So again, not requiring you to have it, but it is something that you can definitely have, okay? Homework, we'll talk a little bit more about this in a minute. It's your responsibility. I am not going to do the homework in the Canvas shell, okay? There are homework problems at the end of the book. They're in your syllabus. You can see what days that we have reading and what problems I have recommended for you. I am not going to grade all of your homework, okay? But I will take quiz questions directly from that homework. So what does that mean for you? What that means for you is that I typically set aside the last 5 minutes of a class for a quiz, of a particular class that we're going to have a quiz, okay? And so what we will do, here, let me get you a copy of the syllabus, sir. I'll say, turn in problem 1A. And if you have that problem worked out in your notebook, all you have to do is rip it out, put your name on it, your ID number, turn it in on your way out. Okay? That's all you got to do. So I highly recommend you keep a notebook, put one problem on each page as best you can. That way you can just rip it out, hand it out on your way in. Okay? And that's going to be your homework or your quiz grade. So all of the quizzes, except for today's quiz, and don't worry about it, it's an easy quiz, okay? Except for today's quiz, will come directly from those homework assignments. Many of those homework assignments have solutions in the back of the book, okay? So, again, it's going to be there to help you prepare for the exam and to also help give you the points that you need to get a good grade in this class, okay? So let me talk a little bit about the course description. The emphasis of this class, this is not the course description in the catalog, but the emphasis of this class is to prepare you for biochemistry CHE 420. Not to prepare you for advanced study in organic, not to prepare you to become a chemist, none of that stuff. It is to prepare you to go to biochemistry 420. You are going to need biochemistry in nutrition and dietetics. Metabolism is a very important thing in that field, right? It's a very important thing in forensics to be able to know what organic molecules are, what biomolecules are. You might be testing for biomolecules in forensics. So this course really does lay that foundation for you to go into biochemistry and understand what's going on there, okay? So that's the goal. But we're also going to talk about some acids and bases. We're going to talk a little bit about kinetics. And we're going to talk about structure and energy. We will talk a little bit about reactions. You know, when you eat food, your body metabolizes that, and that's a fancy word for a chemical reaction. Okay? You need to understand some of the fundamental ways in which reactions occur. It's not magic, right? And so having an understanding of that will certainly help you understand things better in your forensics courses, your nutrition courses, etc. Okay? We are going to cover the book chapters 1 through 14 and 18. Every chapter in the book can prepare you for biochemistry, but I've got so many weeks to cover so much material. Some of it is more fundamental and foundational than others, and I had to make choices. The choice that I made is 1 through 14 you absolutely have to have. The other stuff on biomolecules you'll get in biochemistry, and I think you'll have a good enough foundation to pick up on that pretty quick. But chapter 18 is on amino acids and proteins and peptides. Okay, that's one of the first sets of topics you come to in biochem, and I want you to have a good understanding of the organic chemistry that's involved there. Okay, so that's the reason that I chose those particular chapters. The graded work in this class, we're going to have 3 60-minute exams, and you might note that we are in this classroom for 1 hour and 15 minutes, which means that I am not going to kick you out at 60 minutes. I am writing the exam to approximately be about a 60-minute exam, okay, for the average student. Okay, so that's going to leave a little bit of leeway. We'll come in, we'll have our exam, and won't finish up any lecturing on those days. We will also have a final, which will be a little bit more credit. It will be cumulative, okay? And then, of course, the weekly quizzes that I just mentioned about. So we'll have all of that information, or all of those things that go into your quote-unquote graded work, okay? Now, I want to try to dispel this myth, but everybody thinks that organic chemistry is hard, okay? It is, in my opinion, the most logical, non-mathematical science that exists, okay? I don't think biology comes close. I don't think inorganic chemistry comes close. Physical chemistry certainly doesn't come close because it's heavily mathematical and relies on physics, okay? But there's really about 4 or 5 concepts. If you really know those 4 or 5 concepts, you can do organic chemistry very, very effectively, okay? And organic chemistry is the chemistry of life. Some people will say it's biochemistry, but biochemistry is nothing more than organic chemistry in a living system in water, okay? So I say it's considered a difficult subject. What typically makes it difficult is your study habits. You can easily get behind in organic chemistry, and it will be difficult to catch up. The good news is, again, and I always affectionately call this course, which I've taught several times in the past, baby organic, okay? And it is because we're just not going into it as much in depth. It's easier to catch up in this course than it would be, say, 255 or 256. You can get behind really, really quick, okay? Nonetheless, good study habits are essential to your success in this course, and I have put a study tips sheet in Canvas that you can go and read now, okay? It's actually an essay that was written by Professor Labirko. I don't even know if he's still alive, actually, but it was written back in 1998, and when I found it online years ago, I went, he said everything I hoped to tell every student, okay? So please know that that's there for you to read and to take from it what you will, okay? I do expect when you come to lecture that you have prepared your mind to receive the material of the day. What does that mean? That means that you have at least skimmed through the material. You know what topics we are covering. You've probably worked a couple of the in-chapter problems, okay? You've read kind of the sections. You know what the reading assignments are. All of them are there for the entire semester, already in the syllabus. And barring a hurricane, we are going to stick to that, okay? That's going to be what we're going to stick to this semester, okay? So the class format, you're going to, of course, there's going to be lectures, like me just sitting up here talking, but I don't like to just talk, okay? There will be some small group work throughout the semester on things. You all will get in groups, and you all will work on a number of things that I call kind of like inverted lecture kind of work, okay? Usually it'll take maybe 10, 15 minutes to go through that when we do that. Hopefully we'll do that about once a week. It's important that you all get to know each other and work with one another. That's how learning really occurs. So I'm going to do things like PowerPoint, and again, I'm going to record the PowerPoint lectures like I'm doing right now, post these in YouTube, post them in Canvas so that you can link to them. So all you'll do is you'll find the module with the date of the day of the lecture, and in there will be the link to the YouTube video. They will probably be available by the next day, okay? You got to give me a little bit of time to go in and kind of trim them up a little bit. But they're crude. They're not heavily edited or any kind of fancy work. We will have some concepts tests throughout. I'll give you a question and ask you all to just work through it. It won't be graded. It'll be for me to gauge how well you understand the material as a class. If you all understand that material fairly well, we'll move on. If not, we'll take a step back and we'll repeat. And then, of course, as I mentioned, the weekly quizzes, okay? Class behavior, this goes without saying. treat me like I want to, treat you. All right, let's be nice to each other. Okay. If you arrive late, take the first available seat. Don't disrupt the class. Cell phones or other devices, please put them in silent mode. Don't answer calls during class. Questions should be directed to me during class unless we are in group work, and then I want you to ask each other questions, okay? And, if you're overly disruptive during the class, you may be asked to leave and forfeit their right to turn in any assignments that are due that day. I say that, I've never had to do it. Please don't make it be the first. Okay, so I don't think that's going to be a situation. You all seem like pretty good students. So let's talk a little bit about what you all are concerned about, the course grade. I just want you to remember, I'm interested in what you learn. I'm not interested in your grade. You have to be interested in your grade, okay? But if you learn the topics that I need you to learn, you will do well in this class, okay? They are connected, okay? However, I have had students that learned an awful lot and didn't get the grade to move on simply because they didn't do the work. I can only grade what's there. I had a student one time, not in this particular class, never turned in any homework, even though I did well on the exams. At the end, I was like, well, you got to see. That's how the math worked out. So you need to do the work. Do your part and I'll do mine, okay? So again, we're going to have 14 quizzes, about one a week. They're going to be 20 points each. That's 280 points of the total 780 for the class. That's a good chunk. And again, you know what all of those homework problems are right now. Okay? You will note that in the text, I might have said something like, in the problems, do chapter 1.21. And 1.21 might be A through K. I'm only going to hold you responsible for the first three in those anything that has multiple lines, okay? For a quiz, okay? So you don't have to do A through K. A quiz would be either A, B, or C. So, but they're all good problems, and if you've got time, of course, please do them. Again, 3 regular exams are going to be about 20 to 30 questions. Each one's going to be worth 100 points, so a total of 300 points over the semester is going to be out of regular exams. My regular exams are multiple choice using what's called zip grade, which is, it looks like a little thing you bubble in and I can grade it with my phone. It gives me the grade and all of that stuff real easy. I just take a picture of your thing and it gives me the picture, it gives me the grade, the score. Pretty convenient. You will have to write some stuff on the exam. I will give you a space and I will say right here. Okay? I expect you to write as you're working out a problem. Working out organic chemistry problems in your head is a big, big mistake. I have had situations where people bubbled in the wrong thing and had the answer right on the test, and they brought it back to me and I gave them credit. Okay? So that is in your best interest to use the space that I provide you. We will have a final exam that's worth 150 points, which will be based on the 3 regular exams plus Chapter 18. So basically, if I asked it on the first 3 exams, it's fair game on the final, plus the new content in Chapter 18, or whatever chapters are past exam 3. It's 18, there's maybe 2 or 3 chapters in there. Can't remember right off the top of my head. Okay? Participation, that's going to be worth 50 points. I hope to give everybody those 50 points. That's going to be you working in the group sessions that we have in class. Before each exam, I will have a study session. We will decide on a common time that will work for most of you. I'll also give a few participation points for those of you who come to those as well. So keep that in mind. So the total is 780. All exams, including the final, will be offset such that the highest class score is equal to 100. But I cap that at 10%. All right, so if the highest class score on the exam is a 95, everybody gets 5 extra points added to their exam. So that 95 becomes 100. If the highest is an 85, I give everybody 10 points, and that's how that works. Okay? I used to do this where it was just without the cap, and people got smart and just everybody scored low. That's not what I'm after, right? Okay, so keep in mind that. I want you to note there are no makeup exams. What do I mean by that? I mean that if you oversleep and you miss the exam, there's not a day set aside to make up those exams. If you have COVID, if you are not allowed to be on campus for some reason due to health, illness, whatever, I will work with you. That's not what I mean, okay? Legitimate excuses are legitimate excuses, and I'll work with you to make those up. But unlike some other classes, there are no exam days and then makeup exam days, okay? We just have exam days, okay? So keep that in mind. The grading scale, my philosophy is that the old 10-point grading scale is an archaic thing that has no reality. Why is it that we've always said that everything had to be in 10-point increments and that once you got to 70% or below, you were failing? If I did 70% or better on most of the things in my job, they would think I was a genius. Why do we devote most of the entire grading scale to failure? It never made sense to me. Okay, so I have an expanded grading scale. An A is excellent work, right? And so I keep that from 90 to 100. But notice how I expand the B, the C, and the D range, right? I take a B down to 76%. I take a C down to 65%. I take a D down to 52%. You've gotten the majority of the stuff right in the class. You should pass the class. Okay, now I know you all don't want a D. Nobody wants a D, right? But you would pass the class. You'd be able to move on to the next step. An F in this class is anything below 52%. Okay? So if you go back to that grading scale or those points, right? You know, it should be hard to fail a class. It really should be hard. Everybody who fails my classes, every one of them has failed because they didn't do the work. You do the work, you're going to at least pass this class. I want everybody to know that, okay? Do the work, you'll pass the class, okay? How well you do is how much effort you put in, okay? All right? Nobody wants to go home and put on the refrigerator, I passed the class. They want to put on there that I did really well in the class, right? And that's up to you, and I'm here to help you do that. Any questions on any of that?
No, but thank you.
You're welcome. You got one back here.
On the quizzes, is it just you pretty much need to gamble and do as many other problems as you can for the quizzes, or do you tell us ahead of time?
I do not tell you ahead of time. All I will tell you about the quizzes is that they come from the assignments that I have there, and I will not quiz you on those until we've covered the topics. Okay, so it's not a quiz before we've covered the topic, it's a quiz after. So that's why today's quiz, we haven't covered anything, it's going to be a little different. But let's say next Monday, if I decided to do a quiz next Monday, it would be over chapter 1, whatever's in those problems. Okay?
So it's the following class day, so like the 24th says we're going to cover chapter 1, and then it's got in parentheses all the 1 point so-and-so.
And I'm only going to hold you responsible for those that have multiple sub-problems to the first 3.
So is it the first 3 in every section? So if it's like 1.24, then the first 3 questions there, and then 1.26, the first 3 questions there?
That's correct. Yep.
So it's best to work all of them?
It is.
Um,
It is.
Good question.
Sure.
The website that was mentioned earlier, can you put a link to that in the Canvas shell?
Which website are you talking about?
Darwin.
Oh, Darling Models? Yeah,
Yeah,
I can put that in there, no problem. I'll send that to you. Yeah.
Because I tried looking it up and it went to a very not good site.
Ah, okay.
Does that make sense?
Yeah, it does. I will
I
do
had
it.
to reset myself. I was like, okay, this is sorry.
That's all right. So you all have the syllabus, right? Today, course introduction, we're going to talk a little bit about some general chemistry here in a moment. And again, on the 24th, just as you said, sir, right? Chapter 1, 1.24, 1.26, those are going to be the homework problems that you'll need to work after we've covered the material, right? And you'll see that for all of them. There are tons of problems at the end of the book, but I got to be reasonable, right? So you got more than just this class to do. I know that. But I tried to cover enough stuff to cover all of the topics that are in that. So you at least have a problem over some of that stuff that we do, okay? We will have review sessions before each exam. We've got about a month before the first exam, so we got some time to figure that out. But we'll figure out a location and a time. We'll do this kind of the democratic way, find out what works best for most people. So give you the opportunity to really test me before the test. Okay, so ask me anything you want, kind of. All right, so that's the introduction to the course. Is everybody be comfortable with that? Does it seem fair?
Yes, two questions. So when you say 2 hours a day, would that be 4 hours for each day?
No, basically what, in terms of the study time, that's based on what's called the credit hour definition. So for every credit hour you all are taking in school, the federal government actually expects that you spend that amount of time in class, plus about 2 hours a day, each
So
credit hour.
So 6 hours.
Something like that, yes. For a 3 credit hour class, which this is, right? So you'll be in class for 3 hours, plus in a week, it'll take you about 6 hours to do your reading, your homework. I've actually scaled it back a little bit from that. If you're pretty diligent with your work, it won't take a full 6 hours. But that's kind of about what it takes on average, okay? That's why 12 hours is considered full-time. Because it comes pretty darn close to 40 hours in a week when you do that math, okay? So, I want to talk to you a little bit about organic chemistry. Let's first just think about what chemistry really is. And chemistry is the study of matter and the changes it undergoes. We've got things that Mother Nature has given us, and we know that that changes over time in some sort of reaction, right? Those can be intentional reactions, that is a chemist in a laboratory trying to make new things, new drugs, new materials, whatever the case may be. It could be the nutrition and dietetics part, right? You're given food, which is mostly organic. You eat it. It goes through a series of digestive processes. It gets broken down into things. All of those things are organic chemical reactions, okay? And there are 2 main branches of chemistry, okay? There's organic chemistry, which is what we're going to talk about. And organic chemistry was a term that was coined by this guy named Berzelius back in 1807. So organic chemistry has a long history. Okay, we're not going to go into a lot of the history, but you need to know a little bit. Originally, the term organic chemistry meant any matter derived from something that was living. Okay? So they took a plant, they extracted something from it for like an herbal medicine. That was an organic material. Okay? That is not what we are talking about today when we talk about organic chemistry. Organic chemistry is actually the study of carbon-containing compounds. In particular, compounds that contain carbon, hydrogen, nitrogen, and oxygen. And oh, by the way, carbon, hydrogen, nitrogen, and oxygen are in most of the organic molecules that you all, in the majors that you have, are really focused on, okay? Fatty acids, lipids, proteins. All of those types of things are organic compounds, okay? So having a little bit of an understanding here is important. The thing that I really like about organic chemistry, it occupies a very small part of the periodic table, okay? So it's pretty nice. The other branch, as you might expect, is inorganic chemistry. This is pretty much everything you learned in 106. Originally, this meant matter derived from non-living things, otherwise known as rocks. So we were dealing with rocks, right? It's the vast majority of the periodic table. And I pick on my inorganic chemistry colleagues and say, the entire periodic table is there to create a special place for carbon. Okay? It's a joke, but largely it's true. That special place that carbon takes on the periodic table accounts for all of its chemistry and accounts for why it is the molecule or the element, excuse me, that was chosen for living stuff, okay? Let's talk a little bit about some early organic chemistry. Okay, prior to what we consider the modern era in the mid to late 1800s, there was this belief of vitalism. And that was an early belief that organic compounds could only be prepared by living things due to some unknown vital force. That is, a living thing is because the only thing that could make an organic compound. Okay, and there was some unknown vital force that was responsible for that. And it settled well with people in religion. It settled well with the kings. They were all happy with this definition. Okay? Then along came Frederick Wohler, who is considered the father of organic chemistry. And he actually accidentally made the observation that an inorganic compound could be converted into an organic compound. And that turned vitalism on its head. In a test tube, he was able to take an inorganic compound and make a simple organic compound by the definition of organic back in the day. Okay? He took this compound, which is basically a rock. It's ammonium cyanate. Right? You could go, you could dig it up, you could find it. It wasn't in living things. And he put it in water, and he heated it over a Bunsen burner, and he started to smell something familiar. And this is kind of gross, but it was the smell of urine. It started to smell like urine. What had happened in this, as he heats this up in water, you get urea, which is an organic molecule based on the definition back in the day. If you'll notice, it contains carbon, oxygen, nitrogen, and hydrogen. Right? And it came from living things. They were able to identify this as the main principal organic component of urine back in the day. Okay? That threw vitalism on its head. We now knew that it wasn't just living things that could make, through their biological processes, make organic molecules, but that we as scientists could take what we are given and convert them into organic molecules for other uses. Some of you may also know that urea today is actually used in what's called diesel exhaust fluid. If you have a new diesel pickup truck, you have to not only put diesel fuel in it, you have to put what's called DEF in it. And that DEF is a mixture of urea and water, I believe. And it is used to regenerate the catalyst. So this a simple molecule that still has wide uses today, and they don't make diesel exhaust fluid from urine. Okay, so they actually synthesize this to make a pure compound. Okay, so this started this whole idea of thinking about structure. Right? I think you all can see that this looks very different from that and how things are connected, right? I mean, just by looking at that, you can see that things are different, right? This has ionic charges. There's no ionic charges here, right? Etc. And it looks like the oxygen and carbon and nitrogen are bound together, and then there's another nitrogen that's not even connected to any of those. Clearly a different structure. These are called isomers of one another. You might remember that term from Gen Chem, right? Isomers have the same chemical composition. All of the atoms over here are the same atoms that are over here. They're just connected differently. And again, structure leads to function. That's an important thing, okay? Okay, so how those atoms are connected is clearly different. And so Frederick Wohler's observation eventually allowed organic chemistry to replace the vitalism concept. Okay? We now can go into a laboratory and take what Mother Nature has given us. Usually organic chemists take what is given in terms of crude oil. We take that goop and we make pretty much so all of the medicines that you take. We make pretty much so all of the materials that you're taking advantage of right now. All of the modern materials that are responsible for your computers, cell phones, watches, televisions. We are very much so a petroleum-based species at this point, if you will. Okay? And it's largely because of that simple observation that you could take things and convert them into other. Okay? Now, you're going to need to know a little structural theory. Okay? We can uniquely identify compounds by the precise arrangement of atoms. If we know exactly how atoms are arranged and how they're connected to one another and how they point in 3 dimensions in space, we can start to do something with those. We can start to make predictions. We can start to exploit properties, etc. Okay? So just like I was showing you before, obviously different arrangements of those atoms, right? In that example that I gave you. Okay? There were 3 main players, as I call them, in the early structural theory. This happened long before we had any modern tools to determine structure. Archibald Cooper, Alexander Butlerov, and August Kekulé were the 3 main players in early structural theory. And by early, I mean 1800s-ish, right? I mean, way back in the day. The most important, in my opinion, is August Kekulé. And I got this out of, I think I got this out of Wikipedia about Kekulé. And he's kind of interesting character because he wasn't a good chemist. He was a terrible teacher, from what I understand. But he did have training in architecture. And so what do we know about architecture? It's 3-dimensional. It has structure, right? He used that information or that experience to help develop structural theory. Okay? And in fact, Kekulé told of some waking dream that he had on a London bus back in the day, in which he saw atoms grouping themselves in space. Okay? He thought about this. This was a thought experiment. And basically what he came up were these postulates. That carbon can combine with one another to form chains. So we can connect multiple carbons together. You can have big fatty acids. You can have small fatty acids. Okay? You can have large strands of DNA. You can have short strands of DNA. You can have huge proteins and peptides. You can have small proteins and peptides. Okay? This is the only element on the periodic table that has this ability to seemingly do this out to infinity. I can keep connecting carbons together. And in fact, when we do that, we start to get things like plastic. Plastics have lots of carbons connected together. Okay? They're called macromolecules. Okay? You try to do that with oxygen, it goes boom. You try to do that with nitrogen, it goes boom. You try to do that with anything else, it falls apart or goes boom, pretty much. Okay? Or does something kind of interesting along the way. But it seems that we can just keep connecting carbons together. He also said from his experiences that carbon always had a valency of 4. What does that mean?
4 electrons.
Okay, so it does have 4 valence electrons, that's true. But what does valency mean? We're really talking about the number of bonds it can form. And it can do that because it has those 4 valence electrons. Okay? But it does have a valency of 4. And he also postulated that, you know what? If we study the products of a reaction, that can help give us structural information. People used to believe that was nonsense. People used to say you can't know the structure because anything you do to try to determine it alters that structure. And while there is some truth to that, you can still glean an awful lot of information, okay, by studying the products of a reaction. And the way that I like to tell that story, if you think about it from a forensics point of view, think about being at a crash site. Somebody crashed their car into a wall. You weren't there to see it. You see the after effects of that. You see the parts of the Mustang or the Corvette or whatever strewn across. And you take those pieces and you can start to reconstruct what must have happened at the point of impact. Same thing here. Reactions are kind of like that wreck. We can look at those products and we can determine through careful thought what the structures of the reacting materials probably were. We can get a lot of information by looking at those products. You also need to know a little electronic theory. You learned about this in Chemistry 106. You may not have been told that it's called electronic theory, right? But That's what it is. Electrons are the glue that holds structures together. Electrons are responsible for chemical bonds, right? Chemical bonds are responsible for the shape of a molecule, okay? So this is the glue that holds everything together. In organic chemistry, we are largely talking about covalent bonds, so the sharing of electrons. We will have examples where we talk about some ionic bonding, but in reality, for most of what we do in organic chemistry, it's all covalent, okay? So this electronic theory tells us how our chemical changes can be understood. We can ignore nuclei. That's kind of interesting. The difference between a chemist and a physicist, by and large, is a chemist worries about electrons and a physicist worries about the nucleus. Okay? Now there's some overlap. There are nuclear chemists and there are electronic physicists. Okay? But by and large, the field of chemistry is concerned only with the electrons. And we can consider the nuclei just something to give everything mass. It's along for the ride. Okay? Reactions occur and atoms move because they're moved by the electrons. They want to form a bond. They will move because of this. Okay? Reaction mechanisms come from electronic theory. What do I mean by a reaction mechanism? That's an explanation of exactly how A was converted into B. In general chemistry, you probably took a lot of that on faith. My teacher told me that A plus B gives C. Okay, I take A and B, I put them together, and I see that C gets formed. But how did A and B come together to form C? That's what a reaction mechanism is. How is it that when you eat that piece of bread, it gets digested? What processes are involved? That's a mechanism, okay? Having an understanding of that at a chemical level will help you understand those things later on, I promise. So I want you to understand that our modern world is dependent to a large extent on organic chemistry. Okay? It's important to medicine, ancient and modern. You all had the opportunity to get COVID vaccines because of organic chemistry. You all had the ability to take an analgesic when you ran a fever because an organic chemist helped devise a way to make that molecule. Okay? We make these things using organic chemistry today. Okay? So you think about plant extracts and medicines, the active ingredients are almost always organic compounds. The Native Americans used to chew on the bark of the willow tree when they'd have a headache. It has the precursor to aspirin in it. Okay? It'd give them a bit of an ulcer because it wasn't aspirin itself, but it was the precursor to aspirin. It was contained in those extracts. Prescription drugs are all prepared by synthetic chemists. Your drug companies, Merck, Pfizer, Eli Lilly, Johnson & Johnson, all employ large numbers of organic chemists so that they can take products to market. Okay? It's easy enough to find something that'll work biologically. It's another story to how do I make it on a ton scale so that everybody can have access to it. The perfect example of that is Taxol. Anybody know what Taxol is?
Taxol seems like a compound that used in laboratories to do stuff. I've heard the name before.
You've heard the name? Okay. Taxol is an anti-cancer drug. It's one of the most potent breast cancer drugs we know of, but it comes from the yew tree. You would literally have to decimate the world's population of yew trees to have enough Taxol to treat just a handful of people. So we need to be able to make it from something we have a lot more of, which is crude oil. Right? So we take that, we figure out ways in which we can make things like Taxol. That's what a synthetic chemist does. Okay? Organic chemistry and dyes. This was the first solid link of industry and research. Money derived from research was actually the dye industry. Each and every one of you are wearing something a little different colored today. 200 years ago, that wouldn't have been common, especially if it was purple. You had to kill a lot of little animals to get purple. That's why purple was considered a royal color. Only royalty were allowed to wear it at the time. Nobody thinks about that anymore. You go into a store, you look at something on the rack, And you can pick that thing out in red, blue, purple, yellow, green, and the price doesn't change, right? Because of organic dyes, right? Think about Easter eggs, right? But dyes were a big, big thing. Being able to make synthetic dyes, huge impact on the fashion industry, huge impact on what we wear, huge impact on how we express ourselves, okay? Huge impact on the fact that we're not killing those little mollusks to make purple anymore, right? We can do all that. And then, of course, organic chemistry's played a huge role in our materials development. You think about the modern automobile that we drive, the modern device that we use, our modern televisions, name it, right? Things are important because of organic chemistry, right? So we have synthetic fibers, nylon, right? We have nylon ropes, nylon stockings, so on and so forth. We have synthetic rubber. You know, tires used to have to be made from real rubber from real trees, and that you had to cut them and collect all this stuff and boil it down. We don't do that anymore, by and large. We make the rubber that we need. It's called neoprene, and it lasts longer. You used to change tires, 10,000 miles, they were wore out. You can now go almost 100,000 miles on a set of tires, right? Because of the work that we've done in the materials area. And then you think about all the plastics, right? Plastic jugs, plastic bottles, plastic in your car. Your cars weigh less today and are stronger because of materials that we've developed, okay? So, huge influence on our modern way of life comes from organic chemistry.
I met a few of people who do polymer science. It's very unique. It's like they test like the structures of items. Like if it's like this item is more sturdier due to this compound. It was people who were doing internships here at USM over the summer.
Oh yeah, the summer internships. That's right. Yeah. So let's talk a little bit about where all this carbon came from. It's a little bit of a debate. Not a huge debate. But you can think about it coming from the Big Bang, right? And all of these protons and neutrons that initially happened in the Big Bang started to come together as the universe started to cool. Stars were formed. In stars, they take hydrogen and make helium through a fusion process. Then you start to take helium atoms and you can get carbon, right? Carbon is nothing more than 3 helium atoms that have been smashed together. That happens inside a star. The star explodes, spreads its carbon all throughout the galaxy, universe, so on and so forth, right? It's kind of hard to imagine all of this, but we do know that stars are producing carbon as we speak. They are ginning up carbon. That's what our sun does. Takes hydrogen, makes helium, and then from helium we'll eventually make carbon. So all of the carbon that we have in us came from dying stars, and I find that kind of, we're all stellar dust in a way, and that's really amazing to me, right, to think about that. Okay, so I find that kind of cool, where all the carbon came from. All right, let's talk a little bit about the periodic table in the time that we have remaining. Some other things. So I mentioned to you, right, that organic chemistry was the chemistry of carbon, but also typically we had hydrogen around, nitrogen, and oxygen, right? So these 4 things are typically found in most organic molecules. Now you'll find sulfur, and you'll find selenium, and you'll find the halogens, and you'll find a lot of things in organic molecules. But by and large, the modern definition of an organic molecule is any molecule that contains carbon that has at least 1 bond to hydrogen. So to say that something is organic, it has to have at least 1 CH bond somewhere. Okay? It's kind of the modern definition. And like I said, I always pick on my inorganic friends and tell them that all this other stuff is there just to create these little spaces on the periodic table for the organic stuff, for carbon. Okay? And in a large part it's true. The nice thing about this class, compared to 106, you're not going to have to know much about any of this stuff. You're going to have to know a lot about this, and this.
Essentially what it said is we're not going to use what we use in 06, we're just going to focus on those 3 blue letters up there.
We're going to focus on these 3 letters and hydrogen. That's right. We're going to focus on those. Now, that's not to say the other stuff isn't important. You learned a lot of stuff in 106 about the periodic table that will come into play here. You all learned about electronegativity. right? What do you know about your periodic trend in terms of electronegativity? What happens as you go from the bottom left to the upper right?
Positive, it increases.
It increases, right? We know that fluorine is very electronegative. What does that mean to be electronegative? It means that it pulls electrons to itself, right, in a bond.
It's denser,
Pardon?
denser.
Oh, there is some denser pieces to it, but it's about pulling electrons to itself, right? So we're talking about attracting electrons within a bond, and we'll talk more about that kind of stuff, okay? We know that stuff that's largely on the right-hand side of the periodic table likes to gain electrons. Why? Why does fluorine like to gain electrons? To fulfill the octet to look like neon, right? Neon has a stable shell, right? Its valence shell is completely full. We know that that leads to this so-called noble gas rule, right? Now, you all probably learned about the octet rule, right? I'm seeing a lot of heads nod up and down, and you probably learned it wrong.
Oh no, that does not help.
The octet rule only applies for what?
For ones that have like 16, 106, so.
The second period is,
That's it. Yep,
Yeah.
you were pretty close. This is only the octet. Okay, so carbon will gain electrons to look like neon. It'll gain 4 electrons, right? And it'll have an 8 outer shell. And then you probably learned in general chemistry or your high school chemistry that sulfur has an expanded octet.
Yeah.
Phosphorus has an expanded octet. That's nonsense. Expanded 8? It's either 8 or it's not, right? What is expanded 8? Expanded 8 is 9, 10, 11, 12. It's no longer 8, right? But the octet rule really is about atoms wanting to look like their nearest noble gas. Okay? So lithium isn't going to gain a bunch of electrons to look like neon. It's going to prefer to lose one to look like helium. A lot of chemistry can start to be explained by simply knowing where things sit on a periodic table. And when you look at carbon, what's so special about where it sits? If we think just about electronegativity.
Say the question again?
What's so special about carbon where it sits on the periodic table if we think about it just in terms of electronegativity?
It's smack in the middle.
Smack in the middle. It's in that Goldilocks period, right? Why did I say Goldilocks?
Because it's just perfect.
It's
Not
just
too
right.
hot, not too cold, not too spicy, just perfect.
Just perfect, that's right. Carbon can gain electrons to look like its nearest noble gas. It can also lose electrons. It's at a point where it doesn't want to just strip electrons from everything, but it's willing to share them, which allows it to make these long chains. Fluorine wants to rip an electron from whatever it comes around. Fluorine's a very dangerous gas to work with. You have to have special equipment. I know of people who actually have missing digits because they work with fluorine. It's dangerous stuff. I have all of my digits because I work with carbon. Okay? It doesn't do this, right?
So essentially what you just told us is a helpful warning.
It's a helpful warning, that's right. But basically, that's what you're going to need to know about the periodic table, okay? Let's skip that for an interest of time today. You also need to know a little bit of something about your orbitals and your energy levels. You learned about this in Chemistry 106. You learned about orbitals. What is an orbital?
Orbital is like this, oh, it's like that, orbital is like the shape of the element.
Okay, it is a shape. We've got some shapes up here, right?
Of the
But it's not the overall shape of the element.
protons and electrons.
Protons and electrons do that, yeah.
I think it's the space where the electrons float around.
Okay, it is that's very good, a very good approximation of what it is, all right? It is where you can most likely find a particular electron. It is the space. Some of these are like balls, some of these are like dumbbells, right? So you learned about s orbitals, you learned about p orbitals, you probably learned about d orbitals. The good news is in this class, you don't have to worry about d orbitals, you don't have to worry about f orbitals. All we're going to deal with are balls and dumbbells. Okay?
Wait, what's the other two?
These two, yep.
No, the other two.
These are d orbitals.
So we just simplify the process for us to study. Okay.
Yep, don't have to know those for this class. They are important,
But not this.
but not for this. That's right. So And then you also learned that you have orbitals of different energy, right? And I use what's called the atomic hotel model is how I kind of like to think about it. Now, as he mentioned, what's your name again?
Jason.
Jason. As Jason mentioned, there are spaces where we can find things, right? Well, think about a hotel. A hotel is a space where I can find people, right? Now, if you think about typical hotel when you go to it, not a motel, not the single thing, but a real hotel, right? You have multiple floors, and you have different types of rooms. You may have a ballroom, you may have a regular room, you may have a presidential suite, right? These are all different types of rooms that can hold people. But as you go up in the hotel, in the elevator, you're going to a higher and higher energy level, right? You're either on floor 1 or you're on floor 2 or you're on floor 3. There is no floor 3.5, right? You either get off on floor 1, get off on floor 2, right? This is a quantum thing. This is all the quantum I'm going to throw at you this entire semester, okay? But what you have to know in the atomic hotel is that floor 1 only has one room, and it's this round room called an s orbital. Now, when you go to a hotel, how many people do you typically put in a hotel room? Typically put 2. You
No,
can
yeah.
put more, but typically you put 2. And you put 2 together that kind of like each other. You do not put 2 people in a room that are going to fight all the time. The same thing happens in the electronic hotel, okay? We can put up to 2 electrons in any room, but they have to be spin paired. Remember, one will have to be spinning up, one will have to be spinning down, okay? They have to like each other, okay? So in floor 1, we can have 2 electrons in this room. On floor 2, where carbon lives, the only rooms we have on floor 2 is we have this other round room and we have 3 dumbbell-shaped rooms, right? And so 2, 4, 6, 8. That's where we get the octet rule. If all of these are filled up, you're neon. If all of these only have 1 in there, you're carbon. Okay? And then, of course, you can go to the 3rd floor, which also has a round room, some dumbbell rooms, and all of those D rooms. Okay? So, again, we're not going to be focusing on the 3rd floor. So, really, you just need to know this. Okay?
That looks interesting.
Yeah, we're going to talk a little bit about collision theory. Talk a little bit about kinetics. What comes to mind when I say the word kinetics?
Kinetics means like the transfer of energy.
Almost.
I said movement.
Movement.
I'm supposed.
Yeah, so y'all think about, for those of you who are in kinesiology, kind of think about movement, right? You think something kinetic is moving fast, right? We can have a reaction that occurs such that it produces a product at a particular rate. That's kinetics. If I get a job in an industry and they say, we want you to devise a reactor to make this product, I better not come back to them and say, I've got the reactor and it'll make the amount of product you want in 1,000 years. I'd get fired. I better design a reactor that will give them the product they want on a daily basis, right? Some rate, right? And so that's what kinetics really are. We're talking about the formation of a product over some unit of time, okay? So that comes from collision theory. The theory is that atoms actually have to bump into one another in the right orientation with the right energy, the right speed for a reaction to occur. Not all collisions lead to a reaction, okay? So let's do a quick thought experiment. Let's suppose I took everybody in the room and I took half of you and I put over on that wall and half of you over here on here, and I said a reaction is going to be when you reach out and shake somebody's hand. What could affect the rate of that reaction?
What was the question?
If I took half of you and moved you over there, half of you moved you over here, and I said a reaction is 2 people from opposite sides coming and shaking hands, what would affect the rate at which you can shake hands?
You move way you move.
The way you move, right? So how fast you move,
The number of people.
the number of people,
Distance.
the distance, right? So imagine we've got all of the, there's about 27 of us in here today. Imagine we did that right now, and then imagine if I took you and put you in a room that was half the size. Which one would be faster? This room or the room that's half the size?
Half the size.
Half the size, because the concentration went up. Concentration is very important in reaction kinetics, okay? This is stuff that you really needed to be getting if you had taken 107, and I'm giving you the 10-cent version.
TDL.
Pardon?
Too long, didn't read.
Too long, didn't read, okay. So if you look at this, you've got to have collisions. Collisions are going to be dependent on things like temperature, okay? And they're going to be dependent on concentration, by and large. Okay, those are the two things that are going to be important. For those of you in the health areas, why is it that fever is such a problem? Pardon? It affects, it speeds up your reactions. It allows you to decay faster. That's not a good thing, right? Roughly, and this is an approximation, this is not a law, but approximately every 10 degrees Celsius that a reaction increases, you approximately double the reaction rate. So if you're running a fever that's really high, your reactions are running. You are burning stuff up, okay? Now that's oversimplified, but that's essentially what's happening. You are oxidizing and you are decaying at a much faster rate than you should. All right, let's quickly talk about reaction equilibria. So kinetics is about how fast things go. What is equilibrium?
It means it's completely balanced.
Okay, we're talking about balance, right? Very good. So if something's at equilibrium, so let's just take this silly little reaction. And I'm going to say it's at equilibrium. That's why we have the two arrows. How would I know if that's at equilibrium?
You have to, because the,
I guess there's no more change in either the amount of both the reactants and the product.
All right. So if I have him sample this, and he says, I've got so much A, B, C, and D, and if he comes back tomorrow and he samples it, and he looks again, he says, I have the same amount of A, B, C, and D, and he comes back the day after and he samples it and he says, I've got the same amount of A, B, we're pretty confident that we're at equilibrium. Things aren't changing, right? However, if we just threw A and B together to make C and D, right? At the time we did that, we wouldn't have any C and D. And then we come back tomorrow, we'd have more C and D. We would know that we weren't at equilibrium yet because things were changing still, right? The interesting thing is that living things are not at equilibrium. You are not at equilibrium right now. If you reach equilibrium, you are dead.
yeah,
Chemical systems at equilibrium are dead.
essentially life is constant.
That's right. We call it steady state. You all will learn about that in biochemistry. There is a steady state approximation that says that as things are formed, they are consumed, and we reached a steady state. That is not equilibrium, okay? So equilibrium is about dead stuff. And we express that as Keq, equilibrium constant. Does anybody know what that is equal to? It is equal to the products over the reactants. Always remember that. So it's going to be equal to the concentration of C to the power of little c times the concentration of D to the power little d divided by the concentration of A to the little a times B to the little b. That's the equilibrium constant. If this number is really, really large, what does that tell you about the reaction?
The reaction is going to be pretty big.
What do you mean by that? Pretty big.
Well, if the main product, if the products and reactants have big numbers, it's going to be
Yeah, okay, I got you. Yeah, large numbers for KEQ tell us that the reaction lies to the right.
And if it's
Meaning
put-
that almost all of my reactants have been consumed and made products. Big numbers, just like he said. If that number is small, what does it mean?
It means it's gonna be on the left side.
It's going to be on the left side. It means very little of A and B goes to make C and D. And in fact, any C and D that you make is most likely going to revert to A and B. Any system at equilibrium, the rate of the forward reaction will be exactly equal to the rate of the reverse reaction. So that's little k. We use k too much. And I have trouble drawing little k. So k
Calcium.
and k minus 1. Okay, forward and reverse. All systems at equilibrium, the forward reaction and the reverse reaction have the same exact rate. And that makes sense, doesn't it? Why does that make sense? Because if it wasn't true, things would be changing. If the forward rate of the reaction was high, I would still be forming product. Right? It would be changing. But when that change stops, okay, or at least our observation of that change stops, we know we're at equilibrium. Systems at equilibrium are changing, but you can't tell it. C and D will come together, will break apart to form A and B. But as that happens, A and B are still forming C and D. You can't tell that it's happening, but it is happening. Okay? All right, so we got just a couple minutes left. I want you on this card for your first quiz. This is the easiest quiz you're going to get. I want you to print your name, your ID number, and your preferred name, and or pronouns, however you feel comfortable. And let me know on your way out. Yes, PowerPoints will be on campus. Easiest 20 points of the semester.
I have a question. I noticed you have,
My vitiligo?
yeah,
Yep.
I didn't want it to, I was just curious, so I noticed when you were talking, I apologize.
No, that's fine. No, it is part of who I am. It's a genetic disorder, and one that I largely don't even think about.
So I'm very reserved.
I can tell. That's good.
I try not to show off people. I'm very bad.